the many phases of reliability of deep learning for real-world deployment, organized with my colleagues, André Berserk, Tuan Hong Vu, Sharon Hyun Lee, Deng Sin Dai, Pumet Dukanya, and myself, Patrick. I'm here to introduce the workshop, to say a few words and set the stage, and then I will leave you with the great group of teachers, so to speak. So this is the outline of the tutorial. I will come back to it later. But in order really to get right away in the topic, talking of real-world deployment, I'd like to take this example, which is close to what we do in the Valeo AI team, which is driving assistance and autonomous driving. And this is real world. You might recognize a few cities here. London, Seoul, Tokyo, Paris. Actually, the Parisian photographs are fairly mild compared to how chaotic it can be. But just to give you a sense of, for real-world application in the wild, to give a sense of the complexity and also what is at stake in terms of reliability, because it's critical in terms of safety, obviously. And really to insist on this point, continuing with the autonomous driving example, I borrowed this slide from Waymo. So every year, so Waymo is this robotaxi branch of Alphabet, and every year they publish, or every 2 years they publish their so-called safety report, which is an interesting reading. And in the one from last year, they put up these numbers, and you can see that the car accidents over the world are still making a large number of fatalities, more than 1 million a year, and almost 50,000 just in the US. And the costs for the society is just enormous. So you can imagine that one of the motivation or incentive for doing autonomous driving is to do better, but it also means that it is extremely dangerous, and that then to deploy these things in the open roads, you have to be extremely careful. And as it turns out, still from the report, this is what they claim. They have been driving for real and in simulation in many cities, in many states, etc. So just to say that it's a very serious matter to validate and test these systems before they are actually deployed as a paid service, as it turns out for Waymo now in San Francisco. All right. So as we know, these systems, whether autonomous driving or medical imaging or other things which are safety critical, they all rely on neural networks, and they have massively benefited from the mad progress that we have witnessed in the past decade. And it's great to be in the community also, to be part of that, and to see this incredible progress due to deep learning and new architectures, etc., etc. I just took these graphs of the evolution of the state-of-the-art performance on different typical computer vision tasks on academic benchmarks on the Paper with Code website, which is a fantastic resource. And if you look at the classic ImageNet 1K classification benchmark, you see that we have almost doubled the performance in a decade, which is just amazing. And the same with segmentation on the popular Pascal VOC semantic segmentation benchmark, and likewise for object detection on MS COCO. So we are all aware of that, and we have already started to see yesterday in workshops, talks showing even better numbers, and it will be even more so during the main conference in the coming 3 days. So this is all good. It's really actually fantastic. But here we are talking about benchmarks, which are not necessarily related to real-world application. And in particular, we all know that these models, even if they get excellent performance, they still do a lot of errors, even in the very controlled setting of test, what I call dev test, which is not the real world test, but really what we do when we have our favorite split of train value test, and still there are errors. And it gets even worse when you have serious distribution shifts, which gets us closer to what it would be in real life. And there is some brittleness, which is still very problematic with these models, and this includes, by the way, the brand new generative models that we see to create images and to have dialogue in the chatbots. And in particular, you can have completely absurd, at least from the human eye, completely absurd predictions, which are very hard to understand and not necessarily easy to accept for the society when it comes to safety critical things. And just to take two examples, this is one showing a computer vision driving assistance system being blinded by sun glare and having difficulty with the management of the lane. And another well-known example from the first paper on adversarial attack, where you can, as we all know, switch completely and very confidently the decision of a classifier by adding a well-crafted but very small noise, and vice versa. You can build completely absurd images which are predicted again with high confidence as random classes. So it's a bit worrying, right, when you think of these things in real world. And I can tell you that when car makers realized that, they were a bit nervous about some of the computer vision systems. And one of the problems when trying to get from the lab to the open world is that when you define your system, you define its intended domain of operation. So in the case of a car, if it's a robotaxi, it's for a certain region, it's sometimes for a certain time of the day, etc., etc. And the first thing you do is to gather data to try and cover at best this intended domain. But the actual coverage is always gaps. In particular, and not surprisingly, things which are very rare or very hard to see in real life, in particular if it's dangerous or because it's costly, and you can find that in many application domains. These things are not represented or not enough or not at all in your training data or even in your test data. And this also includes all sorts of perturbations, and because of the adverse conditions, if it is for an outdoor system like autonomous driving, or issues with the sensor. I'm again showing examples from the driving domain, where you see weird marking on the road, including a fake 3D pedestrian crossing. You see on the bottom right the case of a fisheye camera, which is used for low-speed maneuver, which is completely blocked by dirt because of the weather. You see also heavy fog, etc., etc. So all sorts of not so uncommon but pretty annoying situations that can completely defeat your best or top or state-of-the-art system once deployed in the real world. So to recap, when it comes to these AI-based systems that we want to deploy, so we want to have them as useful and safe as possible, there are a few requirements. The first one, obviously, and this is probably the one we strive the most for in the scientific community, is to make sure they are as accurate as possible in the intended domain. Again, the training data can be a bit insufficient, and when I say intended domain, it should include as much as possible corner cases, because they are always corner cases. But then the other thing is that these models should be robust to all sorts of perturbations still in this intended domain, and certainly very important characteristics or features should be the ability of the system to provide, to be aware of its own confidence or uncertainty when it does predictions. And in particular, it should refuse to decide or predict in case of too high uncertainty. And likewise, or related, it should be able to detect inputs which are completely out of its domain of operation. And last but not least, the system should be able to adapt or even to generalize to new conditions, new domains, etc. All in all, what I'm seeing here is that excellent accuracy at dev test time is not sufficient by far. It's a necessary but not sufficient condition. And we should, in order to get these systems out there, make sure that we assess all the phases of the runtime reliability, and of course we try and improve them. And just talking of assessment, I'd like to highlight that there is already, of course, a lot of efforts, and it's a research topic per se. And in particular, things started with some synthetic corruptions and perturbations on ImageNet. Like here you see the ImageNet C for corruption, where there is a synthetic corruption on the validation and test data, and then you can measure the degradation of the performance of your model. In here you have different types, a large variety of corruptions which are synthetic. Likewise, you have also different degrees of corruption. In this case, it's for the noise, which means that you can really track the performance or the drop of performance as the degree of severity of the corruption increases. You have also, for instance, another type of changes, in that case not corruption but perturbation, say the change of the contrast, the change of the gamma, if you want to emulate different sensing characteristics, etc. And same here, you might want to track and compare different models when it comes to the degradation of their performance in the face of these perturbations. Which is all good, and we see that in other fields, including for driving. There are similar things with cityscapes, which comes in different flavor now, with synthetic fog or rain, or rare objects which have been added in the real scenes, etc., etc. So it's very important that we push that. That being said, these are still sort of lab experiments, so I think we need to move from this to real perturbation, which again is not very easy, as I was saying earlier, or at least as realistic perturbation as possible. And the other thing I'm still related to the assessment of the robustness and other aspect, which will be discussed today, is how to measure the confidence of a model, in particular if it's a classifier. We use looking at the scores. So just to put everyone on the same page, why do we care about predicting the confidence or the uncertainty of a model? It serves at two stages. One which is during the development of a model, because it really helps getting a better architecture, but also you might use that in order to do automatic or pre-automatic or semi-automatic annotation with an already trained model, and in which case you want to make sure that you have some sense of the quality of these annotations. So that's very useful. But even maybe more importantly, when you deploy your model, if you have this embedded capability of predicting the uncertainty, then it's good when you validate the frozen model, and then you know what are the most critical situations that you have to focus on in the next development cycle. But of course, it's also important for the actual operation of the model, as I will explain in a minute. And at the end of the day, it's crucial also to get the trust of the users. And more specifically, if the model is able, with good accuracy, to determine that it is very uncertain, that at some point it can be used in different ways. It can be, if the model is just part of a stack of module, then it can inform the next module of its own uncertainty. If you are dealing with the dynamic systems, then things are repeated over time, so you can get, as in the good old common future, make use of this uncertainty to inform the next time step prediction. If your system has multiple sensors or multiple modalities, then you can use that in order to adapt your redundancy on the fly, or raise an alarm to a user, or to give control to a human if there is one in the loop. Typically in an autonomous car, up to a certain level of autonomy, you still have a driver with all the devices to drive the car, so you can disengage the system. Or you can resort to an emergency fallback system. Again, with the car, it might mean that the car has just to pull out. I'm not going to say much about confidence, but just to remind that in classification with deep neural networks, if you just look at the scores of the classes as an indicator of confidence, it can be quite misleading. Again, I already mentioned that adversarial perturbations can be very confidently but badly classified. But on the left, what you see as well is that if you look at the histogram of the scores of your classifier on the test set, and you compare that to the actual and the average of this seen as a confidence, and you compare that to the actual accuracy, there is a gap, and it's called the calibration error, and you will learn more about that. Which brings me to my small roadmap to finish my introduction here. I think it's important, obviously, to be able to assess the reliability of a model, which has to be deployed in a real-world application, in particular if it is safety critical. And to do that, certainly not with a single metric or KPI or criteria. You need more. You really need to look at different angles. This has to be done with as realistic as possible domain shifts and corner cases. Of course, eventually the idea is to improve the reliability, in particular to improve the robustness to perturbations, to out-of-distribution inputs, and then to endow your system with the ability to generalize to new domains. At runtime, as I said just before, it's very good even to predict the confidence of your model in order, in particular, to be able to predict likely failures, to detect out-of-distribution inputs. It might be useful as well to distinguish different types of uncertainties, like aleatoric or epistemic, and to have a rejection option for your model. Well, it depends on the application, but usually it's a good thing to allow the model to refuse predicting. And last but not least, and it's particularly important in the autonomous driving industry, let's make sure that we have the best coverage possible in our data, whether it's real data, synthetic data, or a mix thereof, for the training, and even more for the testing and the validation. With that, I put again the program for the rest of this morning. So you will have Andre, Punet, then a break, Sharon, Detsing, and Chuan Hong, and Andre again, to take you through different aspects of some of the things that I just alluded to in my introduction. Thank you very much.